Okay, so let us start the session. So in today's session, we'll be seeing about 2017 GATE AE paper, that is jet propulsion questions, all the jet propulsion related questions asked in the 2017 GATE AE paper. So let us jump on to the first question. The question here it is more of a thermodynamic related question. So see, consider a system consisting of certain amount of perfect gas enclosed in a cylinder fitted with a frictionless piston. This system can undergo following processes. The process 1, expansion with finite pressure difference with the surrounding. The second process which can undergo is
You are currently the only person in this conference.
Compression with infinitesimal pressure difference with the surrounding. Heat transfer with finite temperature difference with the reservoir. Heat transfer with infinitesimal temperature difference with the reservoir. Out of these options, which process are reversible? So this is very interesting one. See, we have expansion, compression, or heat transfer. That is not the main issue here. The main thing we have to consider here, whether it has a finite difference or infinitesimally small. So by definition, the reversible process are those processes, they are quasi-static. So it has to be slow so that the sudden changes will not occur. The sudden changes means there is a reversibilities which can come into picture, irreversibilities that can come into picture. So the process has to go slowly so that I can reverse it in a way it traced. So any process which has a infinitesimal differences, that can be reversed. So that is why only option which has infinitesimal difference, that is the option 2, compression with infinitesimal pressure difference, and heat transfer with infinitesimal temperature difference. These two can be reversed, whereas the other two, which has a finite difference with the surrounding, they cannot be reversed. So based on this, option D is correct. So the next one, among the following engines, which one is expected to have the maximum specific impulse? You can actually straight away answer this question based on the given options. Let us see the definition of specific impulse more carefully. What is actually a specific impulse? It is defined as, say, IS as a specific impulse, that is thrust produced by the engine to the weight flow rate of the propellant. Right? This is how we define the specific impulse. More precise definition will be the integration of this one. This actually comes with the idea that we have a same mass flow rate throughout the operation. So which can actually written in terms of m dot p dt times velocity. I can either include within or outside, it depends. Let us include within the integral Cj. So this is a more precise form, because here we assume whatever the time duration we are going to consider, 0 to time of burn. So we will consider the mass flow rate and velocity to stay constant. That is why we can take out of the integral and represent in terms of thrust. So it is fine. So for discussion for this question, I can take this form F by m dot p g naught. So now you see, when it comes to a rocket engines, you see all other options, cryogenic rocket, solid propellant rocket, liquid propellant rocket, all three are rocket engines. For rocket engines, what happens? They are not the air breathing engines. We have to carry both fuel as well as oxidizers. So we usually consider mass flow rate of the propellant as the reference. Whereas when it comes to air breathing engines such as jet engines, scramjet, ramjet, turbojet, whatever, jet engines, they are air breathing engines. For them, we don't carry oxidizers. We take oxygen from the surrounding. That is why the only thing we are actually carrying is mass of the fuel that is actually carried by the aircraft. So that will be used in the propulsion. So now when I define for these engines, that effectively becomes thrust produced by the engine to mass flow rate of the fuel times G naught. So now you see this will be much smaller compared to the thrust whatever we are having. So the order of magnitude varies. So here mass of the propellant what we carry, which will be more. That is why the per thrust whatever we are producing to that of whatever the mass of the propellant we are burning will be more compared to the thrust what we produce by the air breathing engine to the mass of the fuel we are carrying on board will be less. So in that sense, specific impulse will be much higher in the air breathing engines compared to rocket engines. So option D. So now if you guys have any question in between, you can raise. Okay. Now we will move on to the next question. That is, maximum gas flow rate that can be handled by a multi-stage axial compressor at a given rotational speed is dictated by. Okay, this is again very interesting question. So if you remember the fundamentals of rotating machines, so we deduced a dimensionless numbers which govern the rotating machines, right? So there we have non-dimensionalized certain important parameters. So we came to a form that, so P naught 2 by P naught 1, T naught 2 by T naught 1, and non-dimensional mass flow rate is given by some form of m dot by root T naught. So there is diameter and rotation speed comes. Diameter and density comes. I am not including here. Okay, so then n divided by root T naught. So this is actually m dot root T naught, something like that. Okay, so this is not what we are interested in right now. But here I can actually plot between different non-dimensional groups. So when I go and plot those non-dimensional group, there is one such graphs we find in any reference which discuss about this rotational rotation machines which are rotating. That is, one of them is like this pressure ratio versus mass flow rate as a n divided by root T naught as a parameter. So now you see this, as my rotational speed increases, this curve shifts like this. So if you understand this curve very carefully, there are two limits for compressor to have a mass flow rate limit. So one is at the point of surging, or in centrifugal compressor it will be usually surging, in axial compressor it will be usually stalling. It's fine. So that is one of the limit. The other limit is going to be the choking. So beyond certain pressure ratio and for a given rotational speed, mass flow rate becomes choked. So after that, you cannot increase the mass flow rate. This is very interesting part. You see, the choking is usually what we discuss in class. Usually you find this terminology in gas dynamics classes when you are discussing CD nozzles. There you define choking is a phenomenon at which mass flow rate becomes constant and for a given upstream conditions of a nozzle. The mass flow rate becomes constant at the throat. At the choking point, you define Mach number becomes 1, it becomes sonic condition and all. That is with respect to CD nozzle. You should not take the message that the choking is always going to be Mach number 1. No. Choking is a condition when mass flow rate becomes constant or further increase of mass flow rate is not possible with the given operating condition. That is what we call it as choking. Okay. So now, if you look at this particular graph, you see for every rotational speed, as we increase the rotational speed, every rotational speed there is a limit, the upper limit. So that is actually limited by choking, right? So you see, the question is asking the maximum gas flow rate that can be handled by a multi-stage axial compressor at a given rotational speed is dictated by. So now if I draw one particular rotational speed, P02 by P01 versus m dot root T naught, some non-dimensional form. So I have a surging line. So I have a curve like this. So this is actually limited by choking. So it is for one particular rotational speed. Okay. So the minimum mass flow rate is limited by surge or stall, especially for axial compressor. Stalling is a serious issue. So stall is a first limit. So I can go on to draw one more line that is for surge. The first line is stall. Okay. The maximum one is controlled by choking. Okay. So somebody is asking a question. For calculating the mass flow rate in a rotating machine, which velocity do we consider? Okay, this is very interesting question. This one is not exactly from the propulsion perspective. You have to uh, trace back your ideas from control volume analysis what you did. So in fluid mechanics fundamentals, right? What is mass flow rate is all about? It is a flux going out of surface or into the surface, right? Any surface you give. So I have a surface normal vector n and some velocity component say v. Okay. So what exactly you are going to consider is, if you remember your Reynolds transport theorem, what exactly Reynolds transport theorem says about? It relates system to the control volume, right? So I have dm by dt of a system which can be written in terms of the volume integral of dou by dou t of rho dv plus, so I'm writing for mass balance, it can be general form also. Okay, then I have a over a control surface, closed control surface, the flux which is going out of the control surface are in vr dot dA, right? So you see, this is actually a vector product. What exactly it says you? It says you the flux which is going out or into the surface based on the velocity vector and the area vector direction, right? If area vector and velocity vectors are in both are in the same direction, then it is the flux which is going out. If the velocity vector and area vectors are in the opposite direction, then the flux which is going into the surface. So it basically, what is the dot product? What is the physical meaning of a dot product? Yes, can anybody say what's the physical meaning of a dot product? What does it signifies? it's a projection of particular vector onto the some other vector, right? If I have a Cartesian coordinate like this, xy, and I have a vector A and I have a vector B. Okay, so if I want to find the projection of vector B onto the vector A, what do you find? That is the angle defined by cosine, right? It's an adjacent side. How much of, you see, in other way, you have one long stick, okay, and another stick you have over here, okay. How much of its shadow is falling onto this particular stick, the stick A and stick B? How much amount of shadow of stick B is falling onto stick A? That is nothing but a projection of stick B on stick A. If you are looking from, so from an engineering perspective, you see it is a top view. Once you look at the top view, how much of this you cannot see, that is covering this stick A, that is the projection of this B onto stick A. That much you can't see. When you draw it on the top view, it comes like this. This much you cannot see, this much of A you can see. So that's how this is your projection of B onto A. That's the same thing. It's a cross dot product of a vectors. So that represents the flux. So here also what you are doing, the velocity dotted with area vector. So n is a unit normal vector to area. So that velocity component you are actually considering for the mass flow rate. So now it's basically represent the flux. That is what you are considering. So now you take centrifugal compressor. Yes. So if I have a centrifugal compressor, so I have a, so I am just taking the bottom half. So I have a mass flow rate which is coming in this direction. Say like it is coming at some direction, absolute velocity c, and which is going with some absolute velocity c2. Okay. So now which velocity vector I have to consider? If I have to consider the, if I have to calculate the mass flow rate at the entry, that is the projection of the C onto area normal vector, that is this one. So if I look at in the front view, that will be like this. So this is my area through which mass can go. So this area can be calculated at pi d2 square minus d1 square divided by 4. This is my area through which mass can go in. So the unit normal vector will be perpendicular to that one. So now my velocity is coming at an angle in a sense. Then the component of that velocity which is normal to this area vector, that is my mass flow in. So for that, if you calculate the component of this velocity vector, so you can basically divide into tangential component CT, axial component CA at the entry. So which one is projecting onto the area? CA. So you consider axial velocity at the entry of the centrifugal compressor. When it comes to a exit of the centrifugal compressor, that is interesting. So if I see the same centrifugal compressor like this, so I have all these impellers. So then if I extend into 3D view, right? So this is the area through which mass is going out, right? So everywhere. So now this is the width of the impeller. This is the circumference total. So the circumference is given by pi into d. The capital D represents the diameter of the impeller at the exit plane. Now the width of the impeller is b. This is the area through which the mass of the gas is going out. That is my area normal vector. Now if I have any velocity vector c that is not exactly onto the normal plane, if I want to project it back, so what are the velocity component I can project it? One is tangential component, other one is radial component. So what exactly I have to consider? the projection of this velocity vector onto the area normal vector will be radial vector, right? So I have to consider CR in the exit plane. So axial flow compressor, it is straightforward. I have absolute velocity coming in. I have a rotor sets. So then the area normal vector will be by d, like if you consider d2 square minus d1 square by 4 is the area through which the flow can go in, and the component of velocity, absolute velocity, which is normal to the area vector, will be CA. So that you consider. I hope I answered your question. Are you clear which velocity vector you are considering? Yes. Okay, so let us move on to the next question. For a turbine stage, which one of the following losses occurs due to the turning of the wall boundary layer through an angle due to the curved surface? This is actually very tricky question. So basically we can have 4 different kinds of losses, the main losses. One is the profile loss, the second one is annulus loss, the other one is the tip clearance loss. Anything other than these 3 is secondary loss. So now we see what are these losses exactly means. So we know that any aerodynamic body we usually use a streamlined body such as aerofoil. So say in a turbine stage, I have a rotor, okay, and the rotor is rotating. So I have a rotor like this, rotating in this direction. So now it will have a particular profile shape, the aerofoil profile, that is given, the shape of the aerofoil is given by aerofoil profile. So along the profile, there is a boundary layer growth. And especially when it comes to a turbines, they are operating in a favorable pressure gradient. The separation of boundary layer is not much of a serious issue as compared to compressor. Whereas compressor, they are already operating in a adverse pressure gradient because you are raising the pressure. So there the boundary layer separation becomes much more serious issue compared to turbine. In turbine, we will be expanding where pressure is constantly dropping. So it's a favorable pressure gradient scenario. But the boundary layer can still develop on the profile. So there is how boundary layer develops. Let us simplify this problem. Say some flat plate. So I have a incoming air. The boundary layer level develops such that it increases its thickness as it moves along the streamwise direction, right? So at some x location, this is x coordinate, some x1, I have this much of thickness. At x2, I have higher thickness, right? So say it is delta 2, this is delta 1, this thickness of boundary layer. So delta 2 will be greater than delta 1, right? So it is common to any other profile if I take other than the flat plate also. As the flow moves in the streamwise direction, so the boundary layer thickness grows. And what happens if boundary layer thickness grows? That means like the effective area through which the flow is going also decreases, and that will result in a momentum loss. That momentum deficit, what we call in normal aircraft terminologies, we will quantify that using the skin friction drag. So that momentum deficit what we get in, we will treat it as a drag. So here the drag is not an issue. The issue here is like, what if the boundary layer separates? If the boundary layer separates, that brings in lot of loss. And the boundary layer itself is, because of the skin friction, we are having this, the skin friction is arising due to the growth of boundary layer. So friction is not an ideal process as long as our thermodynamic process is considered as isentropic process. So we know it is a frictionless process. The moment when the friction comes in, we can no longer treat it as isentropic because irreversibilities are there, right? So because the friction can bring in irreversibilities. The friction basically brings in what? It brings in the diffusion. That means the viscosity is there. The viscosity, thermal conductivity, or mass diffusivity, all of these quantities what we define, say like not mu, alpha is thermal conductivity. All of these are diffusion variables. This means the moment when you consider these variables in your analysis, that means you have irreversibilities present in the process because they have only one direction. They are governed by thermodynamic second law, where they constantly result in increase in entropy. The moment the entropy of the system is increased due to irreversible process, that means you can't reverse it. This is the law of thermodynamics. So this brings in the irreversibilities into picture. So this profile of a blade on which the boundary layer grows, that actually brings in profile loss. Okay, the annulus loss. What is annulus loss? Now, if I look at the same set of blades in a 3D view, say this is my disc upon which blade is mounted. Okay, there is a passage between these two blades that is nothing but an annulus. So see, so this passage is annulus. Again, there is a surface over here, disc surface, over which boundary layer can grow. So whatever losses happens due to a boundary layer growth on this annulus passage, that results in annulus loss. And what is tip clearance loss? This is again interesting because it is, we know this is nothing but a aerofoil shape. So for any aerofoil, we will have a suction surface and the pressure surface. What exactly it brings in? It brings in the pressure difference between the pressure surface to suction surface. The pressure difference, as long as I have an infinite length of this aerofoil shape, I don't see this tip clearance loss. But we know for all practical reasons, I cannot bring in that infinite wing. Even the normal aircraft wing, it is a finite wing. It is not infinite length, right? It's not just an aerofoil which is extending to infinity. We have a finite length of a wing. So every time when I see a finite length, what happens due to the pressure difference between the bottom surface and the upper surface, the nature governs that the flow has to come from it's like flow will pass whenever it see a pressure gradient, right? Whenever I have a pressure gradient, say P2 and P1, so P2 is greater than P1, then the flow moves in this direction, right? So here also it happens, the high pressure fluid from the bottom surface will try to come to low pressure region in the top surface. That is where you see the wing tip vortices in the finite wing. That is how you you see that wing tip vortices. Similarly, in the turbine blades, I have a shroud which is covering this blade, and this is a rotating machine. For that reason, I cannot fix the turbine blade to the top surface. I have to give some kind of a clearance so that there is no friction between the blade and the surface. So for that, I have to give some kind of a clearance. And the moment when I give that clearance, there is a pressure which is pressure difference between the one side of the turbine blade to other side of the turbine blade will create a flow which can pass through a tip. So that is not desirable as far as our analysis is concerned, because that actually takes a different path than the design. The design path is axial direction, but flow is getting three-dimensional. That is not desired. So that losses are categorized as tip clearance losses. Now, what is secondary flow losses? Any losses which can occur other than these reasons are secondary flow losses. Obviously, whatever is given in the question, it is the turning of the wall boundary layer through an angle due to the curved surface. This is absolutely different. This is actually the profile boundary layer which is developed on the aerofoil profile. Now I am having a turbine rotor blades which is rotating, that induces a certain, because you see the fluid which is trapped within the boundary layer has a lesser flow velocity than the axial velocity of the flow which is coming in. So that means this will have a different inertia than whatever the fluid which is outside the boundary layer. So this inertia will still persist within the boundary layer. The mass which is trapped within the boundary layer will experience a different force or different rotational effect than what you designed for. So this axial velocity is nicely balanced because you have nice velocity triangle, which, sorry, for turbine we have a nice velocity triangle which says like how you have to design the blade, right? So beta, alpha, everything you designed it. So this is how it has to go through. So based on that you have the CA. But the velocity within the boundary layer, they are not having the same axial velocity component. That means still u is same, u is not going to change because it is a rotational speed at a distance from the axis. So this is u is basically defined as omega cross r. So no flow related or fluid mechanics, fluid is actually governing it. It is absolutely governed by the rotational speed of the blade and the height at which you are analyzing. So this rotational speed is kind of a constant for a given rotational speed and a given height. So now only the fluid which is going here will experience the different velocity than what you are designed for. So that actually results in a loss because it experiences the different inertia. That is why option D has to be correct. It's why? Because it's the rotation of that profile boundary layer that is not listed in any of these losses, because all three losses we already explained what these losses means. So the fourth one, the secondary loss, because it's a very different from all these three losses. So the best choice over here is the secondary flow loss. Okay. Somebody has a question, option A. It is not option A. Profile loss already I explained. It is just a boundary layer which is developing on the profile. If that brings in the loss, then it is a profile loss. Now that particular boundary layer is rotating. So this loss is coming due to the rotation of that mass which is trapped within the boundary layer on the other direction. It is not just the skin friction, it is the rotation, the inertia part also comes into picture here. So it's a secondary loss. Okay. Okay then. So let us move on to the next question. In a vaneless space between the impeller and the diffuser vanes, in a centrifugal compressor, the angular momentum varies in the following manner in the radial direction. Okay. To answer this particular question, we have to assume certain things. The first thing I am assuming is like the radial velocity vector is going to be constant. It's not going to change. And the other assumption is like fluid, I am treating it as ideal and all. It is fine. So now, what exactly the question is asking? So I have a compressor, then some, I am actually exaggerating. Okay. So some vaneless space, then I have a diffusers. And between these diffusers, I have certain vanes. Say I have some vanes which is guiding the flow. Okay. It's guiding the flow. So this is my impeller blades. Okay. So now it is impeller tip. Okay. So I have some velocity u2 at the impeller tip. I have some radial velocity component CR and some absolute velocity component C at the tip of the impeller. Now the question is, if I take only this section, so if I draw over here, so two vanes, the question is asking the vaneless space between impeller exit and the diffuser, how does this angular momentum varies? So this is in the radial direction, right? If I trace back, this is my center. So this is in the radial direction, right? So if I take it, say at R1 and at R2, if I calculate the angular momentum, whether how it is varying, that's what they are asking. So all we have to understand here is how we define the angular momentum. That is nothing but the moment of inertia into angular velocity, right? That is the angular momentum idea. So we can also show that L can be written in terms of mass mass times linear velocity times omega or r, sorry, radius, right? So now the thing here is the ct into r is assumed to be constant for a design. That is how we try to design. This is a conservation of angular momentum based on which we design these rotating machines. So keeping that in mind, mass of the fluid is not going to change. It's the angular momentum is actually preserved. It is not going to change along the radial direction. One more thing is, like, once you are exiting from the impeller tip, so you are no more rotating the fluid through a mechanical action. So this is done. So all fluid which are within this vaneless space are coming out of an impeller, and you are not imposing any force on them. They are trying to conserve. It's like a conservation of angular momentum. See, you are rotating some stone with your hand, like tying it to the thread or something, and you are rotating. That is conserved, like you are having centripetal and centrifugal nice balance. The momentum, angular momentum, is conserved. Based on that only you are having this constant motion. It can apply to the satellite which is rotating on earth, where you have a nice balance between gravity as well as the centrifugal action. So that is preserving the satellites in an orbit because of the conservation of angular momentum. So similarly, once it goes out of the impeller, so you are no more exerting any force on the fluid. So it is conserved. So you are giving some momentum and you are leaving it. So it is conserved. So that is why it is not going to vary in the radial direction. As long as you are imposing some force or taking out some momentum from the fluid, it is going to be remain constant. So it's a vaneless space, so it is not going to change. Again, the centripetal effect will be there only when you are having some external force which is trying to rotate the fluid. That is not there. As long as it is inside the impeller, you are imposing a force onto the fluid. So that means, like, you are inputting an energy. So once it goes out of the impeller, what is the source of your energy? You are not adding or extracting any energy. That's why I assume there is no losses and all that part, because I am not considering any friction effect or something where you can potentially see a loss in energy. Okay. So you need some source of energy to change the momentum. That is not there. That's the basic principle upon which we are operating all these machines, right? Rate of change of momentum. We want to change that momentum to get some energy out of it or add some energy to the fluid, right? If you are not adding or extracting any energy, how you are going to change the moment? You cannot change. Momentum. You cannot change. That's the whole purpose, right? Like, that is where we studied these fundamentals of rotating machine. rate of change of momentum that contributes towards either compression or expansion of the fluid. Basic principle. So to this one, option B is more obvious answer. Considering no real effects, it's all assumed. Okay. If there are some frictional losses and all, then it can decrease because of the loss. Okay. So now we will take on the next question. In a combustor, gaseous octane and air are to be burned in stoichiometric proportions. If the required flow rate of air is 1 kg per second, what should be the corresponding flow rate of octane? Okay, this is very interesting question. So, chemical balance. So, we know for any carbohydrates, when it is mixed with oxygen and that is nothing but air, right? So we are actually not considering the inert gases which is present in the air. There is 1% of inert gases which can present in the air, but we will neglect it because it's only 1% compared to the proportion of oxygen and nitrogen. What exactly? Like around 21% of oxygen we will see, and 79% of nitrogen we will see in the air. Okay, it's actually 21, 78 and 1% of inert gases, but we will neglect that. 21, 79. Okay, so now what is the combustion byproducts if it is burnt stoichiometrically? That is CO2 plus H2O plus N2, which is coming as N2 only. So now all we have to balance is this one. So X CO2, if it is X CO2, then I have YH, so it has to be Y by 2 times H, right? So then I have to balance what is oxygen. So XO2 plus Y by 2. So I have 2X plus Y by 2 of O. So or else I can write X plus Y by 4 of O2, right? So this much of oxygen I have to make this combustion complete. So this is again going to be 3.76 times X plus Y by 4 times N2 times 3.476. So it is balancing now. So now I have C8H18. So you put that number. So if X is 8 and Y is 18, what is this going to be? 8 plus 18 by 4. So now it is going to be some kind of a decimal number. So it is going to be like 12.5. Will give me 8 CO2 plus 18 H2O. No, not 18. 9 H2O plus 47 N2. Or better way is like, let us multiply by 2 that equation. So it becomes 2 times C8H18 plus O2 plus 3.76 N2 will give me 2 8 to the 16 CO2 plus 18 into 2, that is 36. So 36 means I'm going to have 18 H2O plus 3.76 into 18. So let us keep like this. Now oxygen is 16 to 2 plus 18. So now I can easily write it's 50. So 25 O2. So it is kind of an integer value. So it becomes 94. So now it is completely balanced. So what is stoichiometric fuel to air ratio? So that is written as summation of mass of the fuel to mass of the air, or so how do we calculate molecular weight into number of moles in fuel to summation of molecular weight of individual components into number of moles of individual components of air. So if I use this one, so what happens? It is going to be what are the components we have in fuel? Carbon and hydrogen. So what is the molecular weight of carbon? That is 12 times number of moles, 8 into 2 16, plus what is the molecular weight of the hydrogen? 1 into number of moles, 18 into 2 36. So what is the molecular weight of oxygen? If I consider molecule of oxygen to be O2 and molecule of nitrogen to be N2. So O2 has the molecular weight 32 into number of moles of O2 is 25, plus molecular weight of nitrogen is 28 times number of moles of nitrogen is 94. If you do that, you will get around 0.066, some other digits. So now it is fuel to air ratio. What we are asked to calculate is mass flow rate of the fuel. So this is nothing but mass flow rate of fuel to mass flow rate of air. And mass flow rate of air is given to us in the problem. If you see, it is 1 kg per second of air. So now if I use that one, so which implies mass flow rate of the fuel equal to fuel to air ratio calculated using stoichiometric balance times mass flow rate of the air. So 1 times 0.066, that is going to be 0.066 kgs per second. Okay, so option A. So let us move on to the next question. This is based on the compressor, axial flow compressor stage. The given diagram represents the velocity triangle at the leading edge and the trailing edge at the mean radius of a single stage axial compressor rotor. The stage efficiency of the compressor is 0.8. The stagnation temperature of the air entering the stage is 298 Kelvin, and the specific heat at constant pressure of air for the air is 1005 joules per kg Kelvin. The ratio of specific heats for air is 1.4. Considering actual work in the rotor is equal to the ideal work, the pressure ratio for this stage is equal to. Okay. Whenever we see these kind of question, the first thing we have to note down here what is given in the problem and what is hidden in the statements. The first hidden condition you have to realize here is actual work in the rotor is equal to ideal. What does they actually saying? They're saying we are not using any power input factor. The power input factor is 1. So there is no losses which is actually coming out of the friction. So that is what they are actually considering here. Because they are already given the efficiency of the rotor is 0.8. So if you consider it is isentropic process by seeing this statement, then you're wrong, because you already have an adiabatic efficiency which is defined. That means there is a loss which is coming due to irreversibility. It's not an isentropic process, but what they are trying to say here is we are not accounting for any power input factor, so that is considered to be 1. Okay, that is an assumption they are given in the statement, that is hidden information. What else is given? They are given the velocity triangle. So you can either use this velocity triangle as it is, no problem, or if you want you can convert it to your conventional or comfortable way what you have seen in your classes and all. So inlet velocity triangle and exit velocity triangle. So I have C1, I have W1, I have U, I have U, CA, CA, C2, W2. So this is beta 1, this is beta 2. So you can either convert in this way or you can use that one. So what else is given in the problem? You are given the blade velocity u 200 meter per second. You are also given beta 1, that is 45 degree. You are also given beta 2, that is 11 degree. You are also given axial flow velocity component CA, so that is 160 meter per second, 165. And what else is given? So you are also given the stage efficiency 0.8. You are also given the information for air properties, perfect gas properties 1.4, gamma, Cp 1005 joules per kg Kelvin. And you are also given the stagnation condition at the entry of the stage. So that is 298 Kelvin. These are the things you are given, and you are asked to find out the stage pressure ratio for this compressor. So we have adiabatic efficiency form for a compressor stage given by, so I'm just using the direct form, but you can use from the TS diagram to find out this form if you are stuck. Pi CS gamma minus 1 by gamma minus 1 divided by delta T naught stage. This is actual work, this is ideal work. So now so if I have to represent this in stage pressure ratio, that is was asked, so I can write like 1 plus stage divided by T naught 1 whole to the power of gamma by gamma minus 1, right? So this is known, the gamma is already given. The only thing we don't know is the temperature rise in the stage. So that part we have to calculate. So for that we have velocity triangle information. So we know work done by a stage can be represented as, from Euler's energy equation, U2 CT2 minus U1 CT1. So that gives me, given that U and C are constant in the given stage, so that is given in the velocity triangle. So which becomes tan alpha 2 minus tan alpha 1, or using this relation U is equal to CT1 plus WT1, which is also equal to CT2 plus WT2. So which implies CT2 minus CT1 equal to WT1 minus WT2. So I can easily write tan alpha 2 minus tan alpha 1 as tan beta 1 minus tan beta 2. So it becomes UCA tan beta 1 minus tan beta 2. So if I have to include power input factor, this becomes power input factor times this one. But in the problem it is given, it is 1. So it's ideal and actual. They are treating it is actual is treated as ideal, right? So now this can be also written as Cp times delta T naught stage from thermodynamics perspective. So now we can easily calculate delta T naught of stage as U Ca divided by Cp times tan beta 1 minus tan beta 2. So everything is given in the problem. U is given, Ca is given, beta 1 is given, beta 2 given, Cp is given. Calculates delta T naught stage. You get something around 26.45 Kelvin, and put it back into the equation for stage pressure ratio that we modified from efficiency form. So if I use this one, so I will get something around 1.27, 2 decimal places. That is what asked in the problem, right? In 2 decimal places, yeah, it comes out to be 1.27. Okay. So now we will move on to the next question. This is on turbojet engine. An aircraft with a turbojet engine having an inlet area of 1 meter square is flying at 270 meter per second at an altitude where the atmospheric pressure is equal to 0.9 bar, the ambient temperature is equal to 290 Kelvin, the stagnation pressure and the temperature at the exit of the turbine are equal to 1.6 bar and 774 Kelvin respectively. The specific heat at constant pressure of the burned gases is equal to 1147 joules per kg Kelvin, and the ratio of specific heat is equal to 1.33. Considering the ideal expansion in the nozzle with no losses, the specific thrust produced by the engine is asking in Newton second per kg unit. You have to pay attention. Okay, and in 1 decimal places. So now we see, we'll try to analyze this problem by making a information which looks much more easier for us to analyze, right? So I have a turbojet engine, compressor unit driven by a turbine unit, and I have a air, mass of air which is coming in, and hot gases which is going out, right? So now what else is given in the problem? Inlet area is given to you 1 meter square. Mass of the air which is coming in, it's not given, it is fine. The inlet velocity is given 270 meter per second. Altitude where it is flying, the condition in the ambient is given. Ambient pressure is given to be 0.9 bar, and the temperature in the ambient is given to be 290 Kelvin. And at the exit plane, what else is given? In the exit plane, exit plane nothing is given, but at the turbine exit they are given. So if I call this is 0th state 1, state 1, state 2, state 3, state 4. So at state 4 the conditions are given. T04 is 774 Kelvin, P04 is 1.6 bar. They are asking you to calculate the specific thrust. What is specific thrust? That is thrust per mass flow rate of air. So this we have to be careful. So it is mass flow rate of air. So what is thrust produced by the turbojet engine? That we can easily show that it's nothing but mass flow rate of gas times the exhaust jet velocity, the momentum thrust, minus inlet momentum drag, mass flow rate of air times Ci plus pressure thrust. So if I have to make it to F divided by mass flow rate of air, that is specific thrust, then it becomes mass flow rate of gas. From the continuity, we can easily show that that is nothing but mass flow rate of air plus mass flow rate of fuel. So if I take mass flow rate of air outside, so that becomes 1 plus F times Cj minus Ci plus Pe minus Pa times Ae by mass flow rate of air. So now what we really have to calculate is Cj. The first thing, Ci is already given in the problem. F, which is not given in the problem and no information is given to calculate. I can consider F to be much smaller than 1, so I can neglect it, it's fine. But all I have to take care whether I have a pressure thrust or not to address this part. So the first thing I am going to check is whether the nozzle is choking or not. Okay, if nozzle is choking, then I can have a pressure thrust component. If nozzle is not choking and it's perfectly expanding to atmosphere, then I don't get this part. So first I have to check whether it is choking or unchoking. So to do that, I am going to read the question one more time. They are saying considering the ideal expansion in the nozzle with no losses. That means they are already saying that nozzle efficiency is 100%, and ideal, that means it is isentropic nozzle. So for isentropic nozzle, I can use P0 by Pe as exit pressure plane using isentropic relation me square to gamma by gamma minus 1. So for the choking condition, this has to become 1. That means like I have a convergent nozzle. That is an assumption we have to take unless and until it is specified. The turbojets are going to use convergent nozzles alone, not CD nozzles. One is convergent nozzle. So now if I put M is equal to 1 in the throat, so now I can get P naught by Pc, the choking pressure condition. That is nothing but gamma plus 1 divided by 2 divided by gamma minus 1. So now you have to consider gamma of gas is given to be 1.33. That we are going to consider. Cp of gas is given 1147 joules per kg Kelvin. This we have to be careful. Okay. So if I use that one, gamma as 1.33, I will get this one around 1.85. Okay, so from here I can calculate choking pressure PC is going to be P naught divided by 1.85. So this one P naught is given 1.6 bar. So if I calculate, I will get 0.865 bar, right? So now ambient condition is given. If it is expanding to ambient condition, what should be P naught by PA? P naught by PA is 1.6 divided by 0.9. That is going to be 1.778. So that means P naught 4 by PA is less than P naught 4 by PC, or I know PA is 0.9 and PC is 0.86. That means PA is greater than PC. So PA is already greater than PC. So for this nozzle geometry, we don't have to go till choking, because before it goes to choking, it is seeing PA. So the exit pressure will nicely balance with PA. So it is unchoked. So it is no more needed to expand, because it can see PA even before. So for this nozzle, it is not choking. So it is unchoked. So it is unchoked means there is no pressure thrust, right? So if there is no pressure thrust, my specific thrust is going to be only momentum. So we treated F to be 0. So that is going to be Cj minus Ci. So all I have to calculate Cj. How I am going to calculate Cj? So again, energy equation. It is an adiabatic flow in the nozzle. So T naught at the exit will be equal to T naught at the exit plane of the turbine, or at the entry of the nozzle. So with this one, which is also equal to Te plus Cj square divided by 2Cp. So just energy balance for steady flow. So this gives me Cj is equal to square root of 2Cp times T naught 4 minus Te. And if I take T naught 4 outside, Cj is equal to square root of 2Cp T naught 4 1 minus Pe by P naught 4 to the power of gamma minus 1 by gamma. Again, here Cp is for gas, gamma is for gas. So Pe by P naught 4 is nothing but this one, 1 divided by 1.778, because Pe is nothing but Pa. So if you use that one, you will get Cp 1147, T naught 4 is 774. You get Cj is equal to something around 462. Sorry, 486.02 meter per second, and Cj minus Ci. Ci is 270. So 486 minus 270 is nothing but 216.02. So meter per second. So meter per second and Newton second per kg are same unit. You can cross check. Newton second per kg. So Newton is nothing but force into mass into acceleration, that is kg meter per second square times second divided by kg. So kg cancel, second cancel. It is just meter per second. So they are same unit. They're just given in different form. So now it is 216.02. So they asked you to put in one decimal place, put 216.0 Newton second per kg. Okay, so let us move on to the next question. Air at 450 Kelvin stagnation temperature and at the rate of 50 kg per second enters the combustor of a turbofan engine and is burned with 1 kg per second of aviation kerosene with a heating value given to be 44 megajoules per kg. The specific heat at constant pressure for the incoming air and the burned products are 1005 joules per kg Kelvin and 1147 joules per kg Kelvin respectively. Considering 100% burner efficiency, the stagnation temperature at the exit of the combustor is equal to. This is again a straightforward question. Was given, I have a combustor. Let us draw a nice control volume. So mass of the kerosene is coming here with at the rate of 1 kg per second with the heating value of 44 megajoules per kg. And I have at the entry, the stagnation temperature is 450 Kelvin and which is coming at the rate of air which is coming at the rate of 50 kgs per second. Now mass of the gas which is exiting and the temperature will be stagnation temperature will be T03, that is was asked to calculate. They are also given the efficiency of the burner is 100%, so we will treat the burner efficiency 100%, and they are given Cp of air 1005 joules per kg Kelvin and Cp of gas which is 1147 joules per kg Kelvin. So all they are asking you to calculate is T03. So what we are going to do here is energy balance. So H03 should be equal to H02 plus whatever the energy you are adding, right? Energy addition. So now what is H03? Mass flow rate of gas times Cp of gas times T03 equal to mass flow rate of air times Cp of air times T02. How much of energy we are adding or heat we are adding here? That is mass flow rate of fuel times burner efficiency times heating value. So if there are some efficiency to burner, so that means all of the heating value what fuel carries might not be converted into heat owing to the efficiency, but in this case it is 1, so it's 100%. We can take care of that. So what is mass flow rate of, so if I want to calculate T03, I can just write for T03 equal to mass flow rate of air divided by mass flow rate of gas times Cp of air divided by Cp of gas times T02 plus mass flow rate of fuel divided by mass flow rate of gas times 1 divided by Cp of gas times heating value of the fuel. So put all the numbers over here. I have 50 divided by mass flow rate of gas is nothing but mass flow rate of air plus mass flow rate of fuel. So that is nothing but 50 plus 1 times Cp of air 1005 divided by 1147. T02 is 450 Kelvin plus again 1 divided by 50 plus 1 into 1 divided by 1147 times 44 into 10 power 6. So to calculate this one, you should get something around 1138. Yes, 1138.7. So Kelvin. So let us just see how many one decimal places. Yeah. So 1138.7 Kelvin. That's our answer. That is nothing but exit temperature of the combustion. Okay, so this will be our last question from 2017 GATE on jet propulsion topic. A centrifugal compressor requires 1800 kilowatt of power to compress 10 kgs per second of air. Consider the whirl velocity component is equal to the impeller speed with no slip and no losses in the impeller. If the impeller has to rotate at 1900 radians per second, the diameter of the impeller is to be in meters and with 2 decimal places. Okay, it's an interesting. So see, I have an impeller which is rotating with 1900 radians per second. Very careful observation you have to make here, the units. So it is already given in radians per second, though they are saying the rotates. The rotation, they are already given in angular velocity form. So it is not given in rotation revolutions per minute. It is given in radian per second. So it is very important unit. So there, that means they are already given omega, angular velocity. All they are asking is the diameter of this one, right? So they are also given the power required by the compressor to compress 10 kgs per second of air. So mass flow rate of air 10 kgs per second, it requires to compress this much of air, it requires 1800 kilowatts of power. So we know power is nothing but mass flow rate of air times Euler energy equation. We have derived it, U2 CT2 minus U1 CT1, rate of change of momentum. That's nothing but a torque. So mass flow rate times the torque is going to give you the power. So now we are assuming one thing, that is the flow enters the centrifugal compressor with an axial velocity. So that means CT1 can be treated 0. That is an assumption we have to take here. Okay, no information is given to calculate CT1. So, or for U1, they are not given the impeller I radius. So CT1 is 0. That is what we are assuming, because we are assuming flow is entering axially. Absolute velocity equal to axial velocity. That's the assumption we have. Okay, so that gives me now mass flow rate of A times U2 CT2 equal to power. So now mass flow rate of air U2 CT2, and they are also given no slip. So it is 1. How do we define the slip factor? That is CT2 divided by U2 for radial impeller vanes. So again, the other assumption I am considering is it is radial impeller vanes. So because backward, forward, nothing is given. So we are assuming it to be radial impeller. So I can write slip factor to be CT2 by U2. So now I can write CT2 as slip factor times U2, and if I replace this one, mass flow rate of A times U2 times sigma U2. So now the slip factor is given to be 1. So it goes to mass flow rate of A times U2 square equal to power. So from here I can calculate U2, that is equal to power divided by mass flow rate of A. So power is given 1800 kilowatt. Mass flow rate of air is given 10. So this should give us the velocity, the peripheral velocity U2 as 424.264 meter per second. So now what is U2? So U2 is nothing but in vector, it is angular velocity vector times the momentum or radial distance, right? So it's a peripheral velocity. So U2 can be written as omega times R. So omega is given 1900, r is unknown, u2 we calculated 424.264. So r is going to be 0.2233 meters. So diameter is nothing but 2r, so which is going to be 0.45 meters in two decimal places. I can fill in the answer. Okay, so this concludes our discussion on GATE E 2017 paper related to jet propulsion topic. If you guys have any question, you can pitch in. Okay, Ashish. The question is like, usually in the problems when you are doing, because considering you have to use virtual calculator, try to consider at least 3 decimal places and round off to the third decimal place. Okay. Don't try to round off the first decimal place. Try to round off third decimal is the best scenario, or second decimal. Okay, Tangamuttu. The radial equilibrium analysis is coming from a concept of angular momentum principle. Okay, so it's usually while designing blade profiles, say in compressor. So at the hub to the tip, how you actually design your aerofoil shapes. So you have to have some kind of a criterion. So this radial equilibrium analysis is coming from this angular momentum principle that helps in design of a axial flow compressor blade profiles, or even for turbine blade profile for matters. So there are different theories like free vertex theory, forced vertex theory, and all. So one of the principle what they people use is free vertex theory. There they say Ct into R is constant. That is nothing but what I said in one of the questions while we are discussing, right? The conservation of angular momentum. So this they will consider Ct cross R is constant. So that is one of the theory based on that they consider. It actually comes this balance which actually comes from conservation of angular momentum. That's what the radial equilibrium analysis is all about. Okay. For the gate point of view, you don't really have to worry too much on radial equilibrium analysis. This forced vertex theory or free vertex theory is not a part of your gate syllabus, so don't really worry about that as of now. After gate, obviously you can go and check for your information, but now please don't distract yourself from that part. Okay. Okay, if you guys have no other questions, we can wind up the session here.